Hi all. So yesterday, as you know, we were looking at chemical reactions and the factors that affect chemical reactions. Well, today what we're going to look at is something called conservation of mass. We had just begun to talk about how you balance chemical equations yesterday, and this comes from this law of conservation of mass. Without this law of conservation of mass, chemistry today would not be what it is because we understand now that if you start off with a certain amount of matter, well, you must finish with that amount of matter, and that is fundamental. So bear with us today. There's a little bit to go through, and then we have a number of questions in to answer at the end. Um, you're probably aware that you had a worksheet due for today. What I'm going to do is I'm going to post the solutions to you. You're going to correct them yourself, and you're going to present your work, your corrected work, then for Monday. Remember, next Monday we have a live lesson. Right, what would be a good idea at the moment is if you paused your video and if you had a go at these true or false questions. So write those answers into your copybook. 1 equals true or false, 2 equals true or false, etc. Right, so starting off with the solutions to these. H2CO3 is produced after the reaction between water and sulfur dioxide. That is false. H2CO3 is the chemical formula for something called carbonic acid. So you can't produce carbonic acid from sulfur dioxide dissolved in water because if sulfur dioxide was dissolved in water, there would have to be sulfur there somewhere. A neutralization reaction usually involves an acid and a base reaction. That is true. We call this a redox reaction. So a neutralization reaction where there's an acid and a base, and they will bring each other closer to neutral, which is a pH of 7. A neutralization reaction always yields a neutral pH. That is not necessarily true because what happens there is that's false. So what happens there is you might, let's say for argument's sake, we take one acid like, for example, hydrochloric acid found in your stomach, which has a pH of 2. And if I add to that, we'll say a basic substance like caustic soda, it very much depends on how much caustic soda I add if I'm going to try to bring that down to a pH of 7. So a neutralization reaction is simply where you add an acid to a base and that's it. It brings it closer to a pH of 7, but it won't be exactly 7 unless maybe you have measured things out very carefully. Number 4. The rate of a chemical reaction could also be described as the speed of the production or use of either the reactant or the product. Now that sounds a bit convoluted, a bit complex, but really that is true, and I'll explain why. So the rate of a reaction is so rate in science just means speed, so the speed of something. And when we talk about a chemical reaction, we can measure two things, and it's represented here in this kind of weighing scales here. You could measure the reactants, so the different chemicals that will react together chemically. So let's put this in context. Let's take an example. Sodium hydroxide and hydrochloric acid will react together. So they are the reactants. If you can imagine in front of you, you've got sodium hydroxide plus hydrochloric acid, and an arrow produces. We know that acids and bases always produce water and salt, so therefore H2O and NaCl for salt. So what you could do there is you could measure out the amount of the reactants at the end of that reaction, and that would tell you about the rate. But you'd have to have a time element to it. So say you probably measure how much sodium hydroxide or hydrochloric acid you have, we'll say after 5 minutes. Or you can measure the amount of products being produced after 5 minutes. So how much water has been produced, how much salt has been produced. Okay, so you're either, when we look at the rate of a chemical reaction, we can either measure it by how much reactants we have used up or how many products we have produced. Right, final thing then is chemical reactions can often be sped up by increasing the temperature, and that is definitely true. Right, so there's a summary of those answers. Now, your book might be useful for this to get some background information, but Antoine Lavoisier is the guy really that we're going to talk about. Lavoisier did a number of different experiments, and in his experiments, he tended to get the same result every single time. When he conducted different experiments, what he found was he created an enclosed environment, and what he found was that if I start off with a chemical reaction and there's a certain mass, so remember the amount of mass is the amount of grams that something contains. If I allow, we'll say, 5 grams of hydrochloric acid to be mixed with 5 grams of hydrochloric acid, well, at the end of the experiment, even if I have produced salt and water as a normal neutralization reaction, there should be a total of 10 grams of salt and water. So therefore, whatever mass you start with, you must have the same mass at the end of that reaction. But of course, when we're talking about chemical reactions, oftentimes what happens is that we end up producing like gases, for example, and gases can escape into the atmosphere around us. So for this experiment to work, Antoine Lavoisier, what he did was he created an enclosure so that the gases could not escape, so that he could conduct his experiment. So when we say the amount of mass stays the same, what we really mean is the number of atoms at the beginning of the chemical reaction must be the same as the number of atoms at the end of the reaction. And this comes from Einstein as well, because Einstein said that matter can neither be created nor destroyed. So, therefore, from Antoine Lavoisier's point of view as well, the number of atoms in a chemical reaction cannot change, even if we change them into different products. So, there is a video on this, and I've posted that to the Google Classroom for you to check out about the law of conservation of mass, and it gives you nice little animations just to explain how that works. But really, we could investigate that in the classroom situation in two different ways. Two simple little experiments you could do. Well, the first one here is where you're using ice. And what we're going to do here is we're going to allow a physical reaction to take place. Now, this technically is not a chemical reaction. What you could do is you could take your cubes of ice and put them into a container and then put them on a mass balance. The mass balance is this piece of equipment here. The mass balance, as you know, measures mass. What you could do is just leave the ice cubes in the lunchbox or in the container for a period of time and come back to it and notice if there's any difference in the mass. What you should find is that the mass has remained the same. Now, you could repeat this experiment to look at a chemical reaction. A good chemical reaction, I'm sure many of you in primary school probably looked at creating your own volcanic eruptions in geography. And what you may have done is you might have added bread soda and vinegar together. Well, how about if you added bread soda and vinegar together inside in this container and measured the mass at the start? You leave it for maybe 10 minutes, and what would you find? You would find that the mass is exactly the same, even though the chemical reaction has taken place and all of the products have changed into different things. Well, the mass still remains the same. Why? Because the atoms' numbers remain the same. So the law of conservation of mass, this is how it's worded, but as long as you have your keywords, that's okay. It states that when a chemical reaction takes place, the total mass of the reactants is equal to the total mass of the products. What do we mean by the reactants? We mean by what chemicals are reacting together. So if we're talking about, for example, again, the neutralization reaction, the acid, which is hydrochloric acid, will react with a base, which is sodium hydroxide, and the products then of that are salt and water. Right, but what about this one below? I have a candle starting off as 56.8 grams and it finishes up at 12.7 grams. Does this not break the law of conservation of mass? Well, think about that for a second. Pause the video and think about it. The answer for that is no, it doesn't break the law of conservation of mass because this is I suppose, not a fair experiment. This candle is burning up the wax. This would be called a combustion reaction. A combustion reaction is actually very much like respiration. You start with a source of what we call hydrocarbons. The hydrocarbons react with oxygen, and they will produce carbon dioxide and water. But where has the carbon dioxide and water gone? The carbon dioxide's gone into the atmosphere. The water is as a gas form, so that flies away. So of course the mass is going to decrease because we have converted the hydrocarbons into carbon dioxide, which goes into the air, and water, which has gone into the air. So the mass will decrease. For this to be a fairer experiment, you should have an enclosure around the candle so that that if it changes state, then and it lost to a gas, then at least you can still measure the gas within the container. Right. So this is what I was just talking about there. The wax is an example of a hydrocarbon. You've heard of hydrocarbons before because all, we'll say, fossil fuels are hydrocarbons, like, for example, petrol, diesel, peat, turf, natural gas, coal. All of them are hydrocarbons. They will all react with oxygen in your fire, and they will produce carbon dioxide and water vapor. Right. And as was mentioned here, if we were to trap all of the carbon dioxide and water vapor formed, we would find that the mass of these two substances would be exactly the same. In other words, there was no change in the mass after the chemical reaction. Right, so that is the law of conservation of mass. Let's now look at the actual ramifications for that when we talk about, let's see, when we talk about chemical reactions. Right, what we're going to do here is I'm going to take you through one example of a chemical reaction, a biochemical reaction this time, and we are going to see how it balances out. Right, so what I'm going to look at here is respiration. Might just pause the video there for us, please, and recall what is the word formula for respiration. Okay, so the answer there is that it is glucose. We have plus oxygen will produce for us carbon dioxide, and also it'll produce for us water vapor. Now remember, vapor is a gas. So if I was to write that into a formula style, it would be glucose plus oxygen produces carbon dioxide plus water. Now, what we want to do now, we've written down the word equation for respiration. What we should write down next is the chemical equation for respiration. So that is C6H12O6 plus O2 produces CO2 plus H2O. What I want you to look carefully at is the number of atoms now in this chemical formula. So let's count them out. What I'm going to do down here is I'm going to write this out in terms of how many carbon have we got on the left, how many hydrogen have we got on the left, how many oxygen have we got on the left, and I'm going to compare that to the number of carbon atoms on the right, hydrogen atoms on the right, oxygen atoms on the right. Right, so what we need to do now is count them up. So if you count them up here, how many carbons have we got? We have got C6, which means I have 6 carbon atoms. If you compare that to the right, how many carbon atoms have I got? Well, it just seems to be 1 carbon here on its own, so I could say 1 carbon. If I count the hydrogen, H12, so I have 12 hydrogens there. Write them down. Compare that to the right, I have 2 hydrogens. Compare the oxygens. So I have 2 oxygens here versus, now if I count them out, I have on the right, I have 2 here, and I have also got 1 over here. So that is 3 oxygen. What you probably have noticed at this stage is that this is what we call an unbalanced chemical equation. So I could say that this is unbalanced. This breaks the rules, rather this breaks the law of conservation of mass in its current form. There's no way that this chemical reaction will happen. So what we have to do is we have to create a balanced chemical reaction. So let's see, can we do it? A good starting point for this would be to figure out where there's more atoms are at. So let's look at glucose, for example. Glucose, when we look at it here, there is C6H12O6. Can I make any one of these be equal? Well, how about if I look at the carbon first of all? There are 6 carbons on the left, there's only 1 on the right. So what I'm going to do here is I'm going to try and balance out the carbons. I'm going to put a 6 here in front of this carbon. That would tell me that, in other words, I have to have 6 molecules of carbon dioxide, which means I would have 6 carbon atoms. So now if I rewrite this, I'm going to again want to have carbon, hydrogen, oxygen, and again over on the right there we have carbon, hydrogen, and oxygen. So I've now got, as I said, I have got 6 carbons on the left, I've got 6 carbons on the right. So this 6 not only affects the carbons, it also affects the oxygens. So I've now got 6 times 2, which would give us 12. I don't think it'll sort us fully, because if you look here, there's only 2 oxygens on the left when we talk about... hold on, did I make a mistake there? I did make a mistake there, sorry guys. There's 2 oxygens here and there's 6 there, so rather this should not be 2. This should be, let's see, what would it be? 2 plus 6, 8. Right. So I'm going to let that work away, guys. That's lagging there, but it'll appear on the screen any minute. Right, so let's look at the hydrogens. There on the left, there are 12. On the right, there are only 2. So in order to balance this, what I need to do is I need to make sure that the 12 will match with another 12 over here. So what I could do here is I could put a 6 in front of this water molecule as well. In other words, what we would have here would be 6 times 2, which would be 12. So in other words, what I end up with here in front of this hydrogen is I've got 12 hydrogens. So now I've got 6 times 2, which is 12, and I have 12 over here as well. Now the oxygens need to be balanced out. We can see that they're not balanced right now. We can see if we work it out, 6 times 2 is 12, plus 6 times 1 is 18. There's 18 oxygens on the right-hand side of this equation. How do I know this is 18? Remember 6, and this is oxygen O1, just 1 there. If there's no number, remember you can just write down there's only one of those atoms. So 6 times 1 is 6 plus 12, which will give us 18 on the right. So 18 on the right. Is there any way we can manipulate this that we would also end up with 18 on the left? Well, if you look at it, I have 6 oxygens here. I can't change that right now. But what I could do here is I could try to make this into a number here that might add up to 18. So 6 plus something must add up to 18. So in other words, 6 plus 12 would add up to 18, wouldn't it? But what I could do there in order to get 12 is I could put the 6 here in front of this oxygen. So 6 times 2 is 12. What you should then do is see, is it actually fully balanced? I have figured out that I have now got 18 oxygens on the left and 18 on the right. So let's see, does the law of conservation of mass apply? Have I ended up with the same number of atoms? I have. So it does. And what I can say about this is that one glucose molecule will react with 6 oxygen molecules of oxygen gas and will produce 6 carbon dioxide molecules plus 6 water molecules as well. And that's what you call a balanced chemical equation. In other words, you can't have unbalanced, but you can have balance. And this is why when you're seeing chemical reactions in science, probably in your book or in my notes, you're starting to notice maybe that there's numbers in front of the elements. And the number in front of the elements tells you how many molecules or how many compounds you have in front of you. Okay? Now, this will take practice, of course, and this will be probably the hardest, one of the harder we'll say chemical reaction that you have to balance and solve. But in the next lesson, we will look at loads of different examples of balancing chemical equations, and you will become an expert at it. Okay, so that's it for today's lesson. See the assignment details on Google Classroom.